Hey guys, here to do the last set of problems with you for the packet. Trying to figure out how to get my pin to work again since it crashed earlier. Doesn't seem to want to let me use a pin, but I guess I can make it work without it. All right. Anyway, okay. So I'm gonna do the last two. I'm gonna do number 27 to 29 from the packet. So let's do 27 first. This one is a problem with power, which you've only very briefly mentioned in class because of time constraints. So let's do this one with power in it. There's a 100 watt motor. Remember, watt is units for power. A 100 watt motor is used to lift a 15 kilogram piece of air conditioning equipment with constant speed. How far can the motor lift the load in 5 seconds? All right, now there's a couple ways to find power. Power equals work over time. Power also equal power. You can also find power by doing the force times velocity. But the question is asking us how far can the motor lift the load, right? How far? That's displacement, right? That's x. We're looking for x here. How far can we push the or pull up the piece of equipment? All right, so this is kind of a multi-step problem. We got to really kind of think about what we know, and it's going to be a two-step problem. So we know our power is 100 watts. We know that the mass of the object is 15 kilograms. We know that our time that we're going to be pulling on it is 5 seconds. So with this information, we can actually find the work that's being done, right? We know the power, we know P, we know T, so we can actually find work using our power equation, right? So let's go ahead and do that. So power equals work over time. We know T is 5. I'm going to rearrange this times T both sides. All right, these T's will cancel. So power times time equals work. So power was 100. T was 5. So work is going to be 500 joules of work, right? Just rearrange to find work. Now we can go back to an old, remember we had 3 ways to find work. One of them was change in energy. That's not going to really help us find displacement though, right? Because there's no displacement in there. But remember that work is, oh, sorry, there I go again, getting ahead of myself. There is a way to find work because we're lifting the equipment straight up, right? So what kind of energy are we gaining? Well, we're gaining potential energy, right? We're gaining gravitational potential energy. So the change in energy here is going to be purely gravitational potential energy, right? Because we're going at a constant speed. So the amount of energy, it's going to have kinetic energy, right? But it's not changing, right? Work is a change in energy. Kinetic energy is not changing. It's only gravitational potential energy is changing. Therefore, our work will equal the change in gravitational potential energy. Well, when it was on the ground, the gravitational potential energy is 0. So how high will the object be after 5 seconds? Well, we're going to do 500 joules of work in it. So we're going to put in 500 joules of work in for W. That's going to equal the change in gravitational potential energy, which is mgh, right? So let's plug in our numbers and see what we can solve for h now, right? Which is the height or displacement, right? Same thing. Height, displacement, straight up means the same thing. So mass was 15, g is 10. That's going to be 150. We're going to divide both sides by 150. 500 over 150 is 3.33333. I'm pretty sure. Yep. So that means that h equals 3.3 meters. So that's how high up actually that the piece of equipment will be lifted. Right. So to recap what we did there, right? We realized that the only kind of energy that is changing, as key, is gravitational potential energy. It was 0 in the beginning because it was on the ground, and then it changed to some amount. How much did it change to? Well, it must have changed by 500 joules because that's how much work we did over here. We found that out by using the power equation. So we know we did 500 joules of work. That's what changed the potential energy. We went ahead and used the potential energy equation since we knew everything except for the h, or displacement straight up, and we went ahead and solved for h, right? Got 3.3 meters. Okay. All right. Hope that's good. for you. Let's go to the next problem. The last one I'm going to do on this packet is number 29. Okay. So this one, we have a ball being projected horizontally with a speed of 20 meters a second from a platform 10 meters high. This is very similar to the problem we had earlier. But we'll do one more just to kind of make sure we're good. So the first part of the question asks us, how much time does it take for the ball to reach the ground? This actually has nothing to do with energy at all. This is purely a kinematics problem. Y equals 1/2 gt squared, right? Doesn't matter how fast the ball is going horizontally, that doesn't make any difference. Remember the example I gave 100 times in class. If I fire a bullet from a gun or drop a bullet straight down at the same time, they both fall at the same time. It takes them both to fall at the same rate, assuming I fired the bullet horizontally, which we are doing. In this case, it is being fired horizontally. So, let's see, g is 10, 1/2 of that, t squared, and that's going to equal, how high up are we? We're 10 meters high. Plug in a 10 for y, and we're just going to solve for t. Half of 10 is 5, divided both up by 5, we get 2 equals t squared. Square root of 2 is, I think, 1.41. Let me make sure. Yep, 1.41. So our time will be 1.41 seconds. All right, so it turns out not that part, not an energy question at all. Actually, just a kinematics question. All right, what about part B? What is the ball's kinetic energy when it reaches the ground? Okay, well, for this problem, we're going to think about the change in energy again, right? What kind of energy do we have at the top? We have gravitational potential, and we have kinetic because the ball has an initial speed. But by the time we get to the bottom, all the energy has been converted into kinetic energy, right? So we're going to say, okay, well, how much energy was at the top? Well, we had, let's see, we had potential energy was mgh, so that's, let's do down here. Potential energy at the top was 0.5 kilogram ball times 10 times 10 again for the height, so that's going to be 50. Potential energy is 50. And what about kinetic energy at the top of the building? It's 1/2 mv squared. Mass is 0.5. Velocity initially was 20. Square it. So we plug that into our calculator, and we're going to get 100. All right, so the total energy at the top is 150 joules of energy at the top of the building, which means at the bottom of the building we must also have 150 joules, right? 150 joules of energy. So what about, well, that's it. Easier than I realized. There you go, right? All the energy is being converted, the potential energy rather, is being converted into kinetic as we fall. So all 50 of that potential energy is going to be converted to kinetic energy at the bottom. So we're going to have 150 joules of kinetic energy at the bottom of the hill. I'm not sure even why the problem asks you to find how long it takes. I guess maybe just a refresher for some kinematics, maybe just so you remember how to do that stuff, because it is going to come back to us from time to time. So there you go. That is the last one I'm going to do. Don't forget to do the graphs on your own. Fill those in. Not going to have any spring energy here. So just do the other parts. All right, that's it. So all in all, we did 10 problems total. 1 in class and then 9 in the videos. So hope this is helpful to you. Again, feel free to message me anytime. Be watching the videos, be doing your homework, at home, practicing, so you're prepared for that test, which will be on Thursday. So, all right, guys, I'll see you on Tuesday. Have a great weekend. Bye-bye.